So if you're coming from a higher level language like Java or Python, you might have heard that manual memory management is difficult, it's quite tedious, and it's insecure. Well, today I want to change your perspective on that because I'm going to introduce a technique called arenas, which will completely change your view on manual memory management, because this will remove almost all the problems they usually face with it. So here I've got a simple program. I just allocate an integer a on the heap using malloc, right? Let's say I allocate another integer b, and then I do some work with a and b. And then after that, what we should do to avoid having a memory leak, right? We should free a and b. So pretty simple. I allocate data on the heap, then I free it once I'm done with it. Let's say I forgot to free b. Well, then what just happened here? We've got a memory leak, right? So we just lost, we forgot to free b, and now we're just going to be staying in our program over time, and it might slow it down or cause problems later down the road. So you might be thinking, okay, this is a pretty simple example. I just remember to free b. It's not that hard, right? But the problem is, these issues can crawl on us in more difficult situations where we're not thinking about it. To give you guys an example, I'm going to construct a doubly linked list. So a doubly linked list, we're going to have a node, and this node is going to have an ID. Then we're going to have two pointers. So one pointer is going to be the next node, which is a child node, and one to the previous node that we came from, which is the parent node. So we can traverse forwards and backwards through the linked list. Let's say I create a node, I give it the ID 1, and the parent node set to null because this is the first node in this linked list, and the child node is another node I just allocated here. Then let's say I initialized the second node in this linked list, so I gave it an ID of 2. I set the parent node to be the first node in the linked list, and then I allocated memory for another child node. Now I initialize the child node, I give it ID 3, the parent node is the second node in the linked list with ID 2, and the child node set to null. So this is the last node in the linked list. So visually, what does this look like? Well, we've got 3 nodes with IDs 1, 2, and 3, and this is how they are related to each other, right? Now, where am I going with this? Let's take the example of I want to remove node with ID 2 from the linked list. So here I've got a node with ID 2, and I want to remove it. Well, how would I do that? I'm going to first rewrite the code a bit, so just remove. I just made it a bit more concise so we have more space to do what we're going to do. In order to remove node 2 from the linked list, what I'm doing here is, the current node is node 2, right? Node 2, so this node that the red arrow is pointing on is our current node. Node 2's parent node, the parent pointer, points to node 1. The child node is node 3. So what I can do is I can access node 1's parent node, which is 1, then set its child node equal to node 2's child node, which is 3. So what I've done is I just made node 1's child pointer point to 3 instead of 2, right? So what I've effectively done, I've just removed node 2 from the linked list, right? And now node 1 and node 3 are directly connected. Although we've completed what we set out to do, which was remove node 2 from the linked list, we've accidentally just caused a problem. What's that problem, you may ask? Well, then we forgot to free the memory for node 2 because we're no longer using node 2 anymore, right? There's no need to have node 2 because it's no longer in the linked list. So what we have here with the current code is a memory leak. And you can see that we didn't actually, you might have not thought of that as this having a memory leak because we're just trying to remove a node from a linked list. But if you forget to free these nodes, then this problem can creep up, and over time our programs get slower and you have more bugs in there. So how would you fix this issue? Well, we just free the node. But sometimes you don't remember this when you're trying to solve a hard problem. So it's a bit tedious. Well, then I showed you guys these examples, but you know what's the solution, right? Are there arenas? And what even is an arena, right? What is an arena? What's the point of it? An arena is just a buffer of memory, okay? So there's nothing more, just arena is just a buffer of memory. Let's say I made this arena, which is 10 kilobytes, right? Let's just assume it's 10 kilobytes. It can be any size we want. An arena will have what we call a offset pointer. And the offset pointer just tells us how far the arena is from the start. And I'll explain why we have that and what it means in just a moment, right? Let's bring back the example we had before of allocating integers. So here I'm going to create an arena. I'm going to set a size equal to 10 kilobytes, right? And instead of using malloc, I'll allocate this memory on the arena. So here I use this function called Arena Alloc. I pass in the arena we just created, and I say size of int, and we get a pointer to an integer back. What does this mean? Like, what's happening here? An integer is 32 bits, which means 4 bytes. So when I allocate 4 bytes on the arena, I just move the offset 4 bytes forward. And this is now the new offset. Now what this function will do is going to return the original offset before we called it. So now A is being stored on the arena, right? Because A points at position 0 and the current offset's 4. So we just push the offset forward by 4 bytes and we just return the original pointer. That's how the arena works. That's how you put memory into the arena. Let's look at another example. I allocate B. So B I allocate on the arena again. Now how am I going to do that? Current offset 4. Allocate 4 bytes for the integer. The current offset's now 5. Sorry, it's currently 8. Then we pass back the pointer to the previous position of the offset, which is at 4 bytes, so at the end of A. So now we just allocated B on the arena, right? So A and B are actually being stored on this buffer of memory, which is in the arena. Let's say I do some work with A and B, and now I've decided that, you know what, I'm done doing all this. I don't need A and B anymore. I just want to free the memory, right? Just want to free the memory. I can use something like arena offset reset pointer. So what does this actually do? Well, I'm just setting the offset to 0. Then I can just mem set the whole buffer to 0. So now the buffer is just completely clear. So I can use this arena again, right? So now I have to just keep creating new arenas. I can just reuse the same arena. And we effectively just cleared out the memory for A and B. Now let's say I don't want to do that, and I instead just want to free the actual memory of A and B. Well then, instead of having to do free A, free B, and I might forget something, I just use something like arena delete, and that just frees the buffer itself, right? And that just solved the whole problem of having to think about individual elements and their lifetimes. So the whole point of an arena, right, is to group lifetimes together. So A and B can just be stored in the same buffer. Instead of having to manually remember freeing A and B, I can just free the buffer itself, and I don't have to worry about memory leaks or any of that stuff. So arenas are very powerful and they're very useful. Now let's look at the example we had before of the doubly linked list. So I'm going to instead use arenas instead of malloc to allocate the nodes, and the arena will look like this after I've done all of that. So the offset's 24 because each node is 8 bytes. So 3 nodes, the offset's 24. Now let's say right here I set the child node of node 1 to be equal to node 3. So I just removed node 2 from the linked list. Do I have a memory leak here? No, because node 2 is still on the arena, right? I didn't have to worry about freeing node 2 because it's not an individual lifetime. It's all stored in one buffer, so I can just free it any time, right? So let's say I want to free the memory for the W linked list. I'm just finished with it. What I can do is I can just use arena reset pointer, and I just cleared the whole buffer. Okay, so I just cleared all the nodes off. Or if I actually want to delete the memory, then I just call free on this arena, and that will just remove the arena itself, just clear the buffer. Now you might be thinking, well, okay, I can't free individual elements. Is that what you're trying to tell me? And the answer is yes. You can't free just node 2 or just node 3 off the arena. If you want to free memory off the arena, you free the whole thing, right? The whole buffer. or you can just reset the pointer and reuse the arena again. That's effectively freeing it as well. And this is a misconception people have with free. When I say free node, free A or free B or free this node, what's actually happening there? Does that mean the memory is being freed? What does free even mean? Well, free just tells the allocator, in this case malloc, that this piece of memory is not being used by me anymore. You can do whatever you want with it. Now the allocator might give it back to the operating system, or might choose just to keep it around because you might want to use it again. So this is not actually inefficient really, having to just store those pieces of memory in the arena, even though we're not needing it right now. Because malloc might just do the same thing. It might just keep that piece of memory around and just give it to you straight away if you ask for it again. So this is a very powerful technique, and the thing about the arena is that all those pointers, so like the nodes and A and B, everything is just a pointer on the buffer. So I don't have to worry about freeing individual elements. I can just free the whole buffer, and this prevents memory leaks pretty much. And even if I do forget to reset the arena's offset, or forget to free the arena, I'll have one big memory leak instead of little small ones. Because if I forget to free a single node in linked list, or if I forget to free an integer A or B, then it's hard to notice in the moment what's happening, right? I might have just like leaked 4 bytes here, but then a few seconds later I leaked another 4 bytes, and then over time these little memory leaks build up and they slow down the program, and they're a lot harder to track down because it's just so small. With an arena, if I leak the memory, so to speak, then I will know right away because there's a big memory leak. It's like, okay, I expected this memory to be free, but I'm using a lot more memory than I thought, so clearly I've got a memory leak here, and you can point it back to the arena. So even though we can have bugs like memory leaks, it's not really much of a problem anymore because they're very easy to catch them, very easy to fix. So I hope you guys understood the theory behind an arena. What I'm going to do now is show you guys a simple example how we can set. So here I've just got a simple hello world program, and the first thing we have to use to create the arena is create an arena struct, right? So the arena struct is going to have a buffer, let's say child pointer buffer of some memory. It's going to have a uint64t. I'm using a 32-bit 64-bit unsigned integer to store the offset. So I'll just say current offset, right, of the arena. And then I have another uint64t which just tells us the buffer size. So, right, so how big is this actual buffer? And we can use this information to see if we can actually push more data onto the arena or if it's just full. So the first function I want to create is an arena init function, because if I just create an arena here, I want to have a function to allocate the memory, set up the variables and stuff. It's just nice to have. So I'll create arena init, and we're just going to pass in the arena we have, and I'll just pass in the size we want the arena to be. So how big is the buffer going to be? So I'll say buffer size, right? Then I'll say arena is equal to, you reference it, I'll say the buffer, it will be, we're using malloc to allocate the buffer. So remember, the elements we push onto the arena, they're all pointers to this buffer. And the buffer might be used, maybe stored in the heap, but we've got access to the buffer so we can free it any time. So that's how we can kind of group those lifetimes together and free things all together at once. So we can say something like malloc buffer size, right? Then what we can do is say buffer size is equal to buffer size we've got passed in, and then I will just set the current offset equal to 0. And we don't have to actually do this, this will be fine without it, because by default when we're using this initialization syntax, any member variable which has not been mentioned here will be set to 0 by default. But I just like putting it here just to make it more explicit. So once we've done this, right, we've allocated memory for the buffer, and we just set the variables up as we need. So the arena will now be working. So we say arena, let's pass in the arena, and let's say I want it to be let's create a variable here called, I'll make a macro here called kilobytes, right? Let's take in a value, and that's going to be 1024 times 1024. Actually, not just this. So x times 1024 is going to give us the value in kilobytes. So let's say I want to allocate 10 kilobytes right here. Right. Let's compile this. It works. Okay, great. So the next thing we need is a function to actually push data onto the arena, so we can actually store memory on the arena. Well, not store memory, just store our variables on the arena, which we're going to use. So the way we're going to do that is I have a function called Arena Alloc, right? That's going to take in an arena, obviously. It's going to take in a unit pointer t. I'll explain what that is in just a sec. I'll call this number of elements. Actually, we could say unit 64t instead. So 64-bit integer. Then I have another one, which is going to be the size of each of these elements. So let's say I'm allocating an array of strings. I can say size of child pointer for each. So the num of lm is going to sorry, not the number of lm. The lm size, this variable right here, that will be size of child pointer, and the number of lm will just be the number of strings you want to allocate there. So let's say it will be 10 or 20, and then we can calculate the total size of the allocation just by doing the number of elements times by the element size. Now you might be thinking, why not just do something like here, unit 64t size, and just call it a day. I'll explain why, but it's to prevent a integer overflow. I'll explain what that means in a sec. So let's just finish off the rest of this. Then I also want to have a unit 64t, which is going to be the alignment, right? So align size. And I'll also explain what that means. So the first thing we need to know is this piece of memory, or is the align size a power of 2? Now what is align size? So this is quickly just an introduction to alignment in memory. Whenever you want to allocate memory inside of a buffer, or let's say using malloc does this for us, but what we have to do is the piece of memory we are allocating has to be a divisor of the natural size of the type. That's a lot of fancy words, right? So what does that mean? Let's say I'm allocating a child pointer. That's 8 bytes, right? And let's say I'm on memory address 1050. Let's say we're on memory address 68, right? In order to allocate memory so that the CPU can efficiently read the memory, the point where you're actually allocating the memory from, it has to be divisible by 8. So this should be divisible by 8. This should be equal to 0. Now currently 68 divided by 8 is not 0. The closest version we have is 64 bytes, but we can't allocate 64 bytes because then we're just losing 4 bytes we already had. So what we just do is we add 4 bytes from the original offset of the arena. So now we've become 72 bytes. So these are padding bytes. Then when we divide by 8, this gives us 0. Then we can allocate memory from memory address 72, right? So the reason we have this padding is so that the memory address we are allocating from is divisible by the align size, right? But another property of align size is that it has to be divisible by 2. Now, why does it have to be divisible by 2? That's just how CPUs work. I don't want to get into alignment because it can get a little bit complicated. But just know that we have to make sure that align size is divisible by 2. Because if it's not, we can have some problems. So in order to support natural alignment, what we have to do is first check that the align size is a power of 2. So how can we do that? Well, the first thing is, if align size is equal to 0, then obviously it's invalid, because 0 is not power of 2. And also we need to make sure that align size itself, so if align size is 0, then if you try to check if it's a power of 2, it's going to return a valid value, because it's how the division works. But the other option is that align size is a valid value, so it's not 0. And we need to check if this is a power of 2. So how can we do that? Well, there's a bit trick we can use, which is align size. We're going to AND on it, and then we do align size minus 1. And if this is equal to 1, then align size is not power of 2, right? So we can say this, or so if either of these are true, then align size is not a valid value. It's not a power of 2. And we just return no there. Otherwise, we can carry on what we're doing, right? So I'm going to create a uint pointer t. I'll explain why we're using uint pointer in just a sec. I'm going to call this allocation size, right? Allocation size is going to be equal to the number of elements we're going to allocate and the size of each element, which is an m size. Now, one thing that can happen is, the reason I separated these two into 2 different values instead of just having uint64t size, which is the number of bytes we want to allocate, is because sometimes, if we're not careful, we can have an integer overflow. What this basically means is the value we end up storing in the allocation size is so large that it overflows the buffer, it overflows the integer, and then we end up getting a negative value or 0 stored in it. So by separating num of elements and element size, we can pretty easily check to make sure that if there's an overflow going on. Because when you have an overflow with an integer and then you pass it around a function, you can have some issues because you might not detect it. So here we can just do the calculation ourselves and then make sure that there's no overflow happening. So how do we check if there's an overflow? Well, if there's an overflow, this uint pointer t should turn negative or 0. So what's going to end up happening is allocation size will end up being less than, let's say, element size. Or it also beats the number of elements, right? Because in that case, it's going to end up overflowing. So we just return no in that case, right? So here we've checked to make sure there's no overflow happening. And now what we can do is we can actually allocate memory onto the arena for this variable. So the current thing we have to do is get the current offset, not just from the arena, but the arena's position in memory plus the offset of the arena. So I'm going to say that's called the current offset. Actually, let's say total offset is equal to cast the arena's current offset. And then I'll add that to uint pointer t arena buffer. So what does uint pointer t actually mean? So by default, a pointer is a 64-bit integer, right? It's in hexadecimal. So this uint pointer t just stores it as a decimal value, so you can do some arithmetic on it. So to get the total offset is basically, let's say arena's buffer is at memory address 100. And then our current offset is, let's say, 20. So if I try to use 20 as a value to find the alignment from, so let's say I'm trying to allocate an integer, or let's say I'm trying to allocate some 8-byte value, then if I just use the arena's buffer value, then it might be incorrect because it's not actually from the start of the memory, it's not actually it's not actually divisible by the alignment size we need. So by doing arena buffer, by doing this calculation right here to get the total offset, what we're just doing is adding the offset of the buffer and the current offset in the arena. So we end up getting 120 in total. Then when we try to get the alignment from there, we get the correct value. So now that we have the total offset, what we can just do is after calculate the padding, right? So the padding is just how many bytes we need to add potentially to this total offset so that it's divisible by the alignment that we need. Now the way we can do that is, let's say, total offset modulus align size. This will tell us how many bytes we need to. This will just tell us how many bytes we actually need to get to a valid memory address to push the memory onto the arena from. We can also simplify this. Let's not simplify this. So the modulus is quite expensive operation, so we can use some bit filling techniques. So we can say total offset plus 1, and then we run and align size minus 1. And this is the same as using the modulus, but since we're using this bit shifting techniques, it's slightly less expensive. So per allocation is slightly faster. So we can just add the padding to the total offset, right? This is going to give us the memory address we're going to push this piece of memory onto. Now what we also need to check is this So is this is a total offset plus allocation size. So can this allocation fit inside the arena? So let's say we've got 10 bytes left in the arena. That's the total amount of memory we have left in the arena, and we try to make an allocation which is 20 bytes. That will go past the maximum size of the buffer in the arena, so that allocation is invalid. We have to check to make sure that the allocation fits inside of the arena. The way we can do that is by doing if the total offset plus the allocation size is going to be greater than, say, unit pointer t arena buffer size plus unit pointer t So if you're checking that if this memory location is greater than the end of the buffer, so the actual the last memory, sorry, if we did this allocation, the new memory address of the offset of the pointer, is it greater than the maximum memory address of the buffer? So once the actual end of it, if that happens, that means that we can't fit this allocation inside the buffer. So we just return this. So we just return no, we can't allocate in the arena. If it is successful, so this is a valid allocation, it can fit inside of the arena. We say the current offset of the arena, we're just going to add that, we're going to add padding plus allocation size. Right? And then total offsets currently pointing to the starting address of this new allocation. So I'm just going to mem set all of that to 0. We don't have to, but I just prefer doing it this way. So we say total offset 0 allocation size. And then we can just return a void pointer to the total offset, right? Let's see if this compiles. Oh, it just compile. So we can do here is something like int a is equal to Arena Alloc, right? Then you have to pass in the arena. Number of elements is going to be 1. Size of each element is integer. Say align size, we can set that to be equal to use the align of operator and just pass in integer right here. And then we get in then we can allocate the integer. So if we run that, let's say a is equal to 20. Right, then just printf. And yeah, that works. So as you can see, you can allocate some memory onto the arena. Let's say I wanna allocate a string. So say we'll make a string of 100 characters. So we're gonna allocate 100 characters there. Make sure the align size is correct. Then I can use something like star copy into a. Let's say a string. And that works fine. So the last thing I want to show you guys is how we can free memory or just reset the arena's pointer so we can reuse it again. So we can say something here like void arena reset pointer. I pass in the arena, right? Should be arena pointer. So what I do here is just set the current offset equal to 0, then just mem set the whole buffer of the arena to 0. So I just say arena buffer 0, then arena buffer size, right? And if I want to actually free the buffer itself, I can just do something like here, I'll call this arena delete, and then instead of just mem setting the buffer to 0, I just free the actual buffer, right? So that should get compiled. So let's say I do arena reset pointer, pass in the arena. Then if I try to print the string out again here, I'm just going to get empty characters because the whole buffer is now just set to 0. So the string's no longer being stored there, or it's been overwritten. If we do something like arena delete, let's try printing out again. I'm just going to get some random characters every single time, because now we no longer have access to that memory. It's been given back to the heap allocator, so in this case malloc. It can store whatever it wants in there, so we shouldn't actually be trying to access it anymore. So I hope you guys enjoyed this video. If you did find it useful or informative, please leave a like and write a comment. If you got any questions, I'll be happy to answer them in the comments as well. I will leave some links to some articles which you will probably find useful if you want to dig into this further. And yeah, I made some videos before about hash tables and dictionaries, so if you like this one, you probably like those ones as well. So thank you for watching. Please like, share, subscribe, and I'll see you guys later. Bye.